So this problem, they have us finding the irreversible head loss of the system. We're given that it is water with a kinetic energy coefficient factor of 1.05. So how we kind of start solving this problem is using the energy equation. And I'm going to be using the head form because that's the one that I've been using the most and it works really well. The unique thing about the head form is that all of our answers will be in meters. And the reason why I like that is that it kind of gives us room to play around with it in terms of getting it into pressures, getting us into really whatever we need to do. We can just multiply, rho g to get pressure, or do anything that we might ever want to do with that. Meters is a very nice unit to work with. So how I like to approach any of these problems is going through the equation one term at a time and seeing what we actually need. And as we go through, I will go ahead and explain kind of what each one of them does. So starting on the left, it says pressure 1 over density times gravity. So we are given a pressure at this location and density is known. We have water. That term is perfectly good. We're good down here. Alpha 1 times velocity 1 squared over 2g. So I said it was the kinetic energy correction factor. It's kind of a mouthful, to be honest. What does that actually mean? So the kinetic energy correction factor essentially is in the fact that if we have something like a wing, imagine this is a cross-sectional area of an aircraft wing, and we have some kind of line going over it. This is a streamline, which, just a very quick side note, all of these areas I'm highlighting on the equation are from the Bernoulli equation. And what that allows us to do is analyze the flow using one of these streamlines. So that's a really useful tool, makes just general fluid analysis a lot easier to work with. But so let me get that drawing back up there. For this alpha term, it would take into account any kind of, maybe some small friction effects, or maybe there's some eddies forming inside the fluid flow around the wing, or maybe inside the pipe, just going up to this pipe picture. Maybe there's a little bit of just turbulence here and there. So that's what this alpha term kind of does. It kind of groups all that together, adds in a little bit more to make it so that our equations will be more true to life, if you will. So in this case, we are given a correction factor of 1.05. So I'm just going to set alpha 1 and alpha 2 just to be alpha. So both of these is this, and we're just kind of given that. Now for velocity 1, sure, we can find that for in here. I mean, we're given our volumetric flow rate. Volumetric flow rate is equal to velocity times area. We can find that, and we should actually be able to find V2 as well using the conservation of mass. Moving forward, we have our Z term. In our Z term, it stands for elevation. And in this case, we have a horizontal pipe, so our Z term will actually go to 0. So Z really depends on the system that you have. You have something where you have like a dam, maybe. And imagine you have a turbine generator system inside of here. Then maybe your Z1 would be down here and your Z2 would be up here. Maybe in this case, I would set my Z1 to 0 and then have Z2 be this entire distance. But in our case, our Z's will just be 0. H pump U. In this system, we do not have a pump, but what this essentially is our useful pumping power. So that's found using efficiency. So that's a whole other little segment, but currently we don't have a pump. Pressure 2, we are given, and just want to make it kind of clear right here, everything inside of this green area I am kind of dotting around, this is our analysis zone. So we don't have to worry about atmospheric pressures or anything. We are given our pressures, which is very, very nice. So we're good there. Same conversation with V2, conservation of mass, we can find that. Alpha, we're given that. Turbine, this is turbine E. We actually do not have a turbine on this system, but H sub turbine E is the extracted energy. With a turbine, the pressure will drop and the turbine will extract some energy from the fluid moving through it. And that would power something like a generator. In this case, though, again, we don't have a turbine. We don't have to worry about that. And head loss. We are actually supposed to find the head loss for the system. So this one is what we are going to try to solve for. And what head loss is essentially just lost energy, if you will. So it's going to be described in meters, which is good, but if we end up multiplying H sub L by rho G, then we can actually get maybe a pressure loss, right? It's a very versatile way of displaying this information where we can just multiply things into it, get stuff out. It's very nice. So head loss is essentially how much energy we're losing in the system, just in a very short blanket version of it. So at this point, we can see what we're solving for, what goes to 0 and why. Our pressures, our velocities, all very nice looking. So let's just kind of start solving this out. I'm going to start by doing velocity. So we are given our volumetric flow rate, which is V dot is equal to VA. And we are given water. And water is really important right here because water is an incompressible fluid. So we can say m dot 1 is equal to m dot 2. This is just the conservation of mass. Where this is rho VA is equal to, again, rho VA, but just further down the system. Well, how we can also write this, as you can see over here, VA and VA is just rho 1 volumetric flow rate 1 is equal to rho 2 volumetric flow rate 2. So with it being incompressible, that means our density will not change. So we can cancel out our densities, which means that we can use this one volumetric flow rate up here to find the velocities at both this area and this area of our system. So let's go ahead and just do that. Oh, I can save that as a picture? Oh, that's kind of cool. Okay, so let's do V1 first. So V dot over A1. And our V dot is given as 0.04 meters cubed per second. Divide that by an area of a circle. So our cross-sectional area over here So this is diameter 1, 0.15 meters. 0.15 meters squared. So this is just another pi r squared, but having the diameter in there instead of the radius. So this should give us our velocity in this part of the system. So 0.04 over pi over 4, 0.15 squared. So this gives 2.26 meters per second. In V2, it'll actually be a really, really similar story. Because remember, conservation of mass and incompressible flow, so we're allowed to use the same volumetric flow rate. But all we have to do is change our diameter. Now, focusing on this part of the system, our diameter is right on over here, 0.08 meters. 0.08 meters. So putting this back into the calculator is 7.96. 7.96 meters per second. So we have our velocity set, and the last thing I do want to do before plugging everything in and solving for H sub L is changing our pressures right up here into pascals. And the reason why I want to do that is we'll have a really nice unit conversion eventually. So if we say that, let me actually just do one of these, 480 kilopascals is equal to 1,000, or there's 1,000 pascals in 1 kilopascal. Then we can cancel out our kilopascals and give us 480 times 1,000, which is, I know, very shocking, 480,000 pascals. Now, just going into the units of all of this, I'm going to be looking at just this one unit conversion. So what I'm going to do here may look a little bit odd, but it'll just kind of make sense as we kind of go along, so you just kind of have to trust me on this. I'm going to be writing out each of these values as their units. So we do a pascal over a kilogram per cubic meter times a meter per second squared. But you have to remember that a pascal is a newton per meter, or a newton over meter squared. So, as that is force over area. So 1 newton is 1 kilogram per meter per second squared, and we still have this thing hanging around. So now we can go ahead and cancel our units. This is all, again, just pascals up here. Down here, this is our density. Down here, this is our acceleration. So we can just kind of start canceling out things. And we are left with our answer in meters, which will actually, work out really well. We want our H sub L in meters. So that's why I'm converting stuff from kilopascals into pascals right here. So in this area, wherever it may be, we'll have a similar kind of story, but it's already kind of set up for us. We have standard units of meter per second for our velocities right here, so we should be pretty good to go. So let's solve for H sub L algebraically. So I'm just going to do that real quick. So H sub L, I'm just going to subtract P2 from both sides. So let's do P1 minus P2 over rho G, just grouping those together, plus alpha over 2G, and then V1 squared minus V2 squared. Again, just subtracting this and this from both sides of the equation. Our alphas are the same now, so that's why I just kind of put them over here. Our 2G's, I just factored those out from underneath the velocities, and now we can just kind of plug in. So our P1 is 480,000 pascals minus 440,000 pascals. So 440,000 pascals. Divide that by the density of water that we have, 1,000 kilograms per cubic meter. Divide that by gravity, 9.81 meter per second squared. Now we are adding 1.05, this is our alpha value, over 2 times gravity, meter per second squared. Actually, let me just put this on another line. Just make a little bit, I don't want to be too cramped. Oh, what did I do? Am I just bad at using an iPad? Apparently, I might be. Okay, there we go, now it races properly. So 1.05 over 2 times 9.81 meter per second squared. And now all of this is multiplied by our velocity 1, which is, so just change that to velocity 2 earlier. So velocity 1 is 2.26 meters per second squared, and we are subtracting V2, which is 7.96 meter per second squared. Excuse me, meter per second, that whole value squared. So this should be our H sub L value in meters. So putting this in the calculator, 480,000 minus 440,000 over 1,000 times 9.81. And then our correction factor, and then 2 times gravity, the denominator of that, and then multiplied by 2.26 squared minus 7.96 squared. And that gives us a head loss of 0.9, I'm just going to round up to 96. 0.96 meters. So that should be the final answer.